Alright, I'm recording another video for 13. So last time we started a new topic, rotations, and we learned that to describe rotations is easier to use angles instead of distance, because if you pick different points on a rotating object, not just an edge, right? Then the distance each point travels is going to be different, right? So if you want to use distance, you have to specify the point. But every point is going to always rotate the same angle, okay? So if I say this object has rotated 30 degrees, you know what I mean. I don't need to specify a point. So it's easier to use angles instead of distance and rotation, to describe rotation. And then the SI unit for angles is the radians, okay? It's not the degrees we have been using, but there's a conversion between them, and you can figure it out. You don't need to remember that, right? As I said, physics is not about remembering equations, right? You understand the definition of the angle in radians? It's always going to be arc length divided by radius, right? And then use one full revolution to connect the degrees and radians, because one full revolution is going to be 360 degrees. And what is the arc length for one full revolution, one full circle? That's going to be circumference, right? Circumference divided by the radius, you will get 2 pi radians. Then use this conversion, you can go from degrees to radians or radians to degrees, just like meters and miles, okay? And then we defined angular velocity, which is equivalent to the linear velocity we defined before. We can use this to describe how fast something is rotating, right? The unit is going to be radians per second. We also defined angular acceleration, which is the equivalent to the linear acceleration we defined before. Then we can use the angular acceleration to describe how fast the angular velocity is changing, right, in a rotating object. And then the relation among these three guys is going to be exactly the same as the relation among these three guys, right? Because if you look at this, the variables we define on the left and the variable defined on the right, if you don't know what these symbols mean, if you don't know what x, v, a mean, you don't know theta, what theta, omega, alpha mean, you look at these two lists, you would say, they're exactly the same to me. I just don't understand why you just write the same variables just using different symbols, right? This is pretty much like this symbol, and this guy is just pretty much like this symbol, and this guy is exactly like this symbol, okay? That's why we define them this way, so that the relation among these three guys is the same as the relation among these three guys. So when you do kinematics, when there's a constant, when something is rotating with a constant angular acceleration, you do kinematics the same way we do with the linear, something's moving in linear motion. All you need to do, if you take a look at the linear kinematic equations on slide 3, lecture 14, we're still on lecture 14, they're exactly the same, right? All you need to do is just replace all these symbols in the original kinematic equation with these new symbols we defined, right? Then everything is the same. And we don't have x and y components in rotation, which is actually easier than this, okay? So, and then you're going to see this a lot in this part. We're going to make a lot of new definitions. We're going to define a lot of new things so that we can just use the theories and laws we learned in linear motion, okay? We don't have to make new theories, new laws, but we will define a lot of new things, and which can be very non-intuitive to a lot of people, okay? The first time I studied this part, it was also very hard for me, very weird, very non-intuitive for me, okay? But again, whenever you learn new things, just practice and practice, and then you will get comfortable working. You will work with these guys, these symbols, okay? Very comfortable as you work with these guys, okay? So of course we will do some practice, but before that, let's take a look at slide 4. So when something is rotating, you pick a point, right? You pick any point. Well, it's still traveling some distance. You can still say a point is traveling like 20 centimeters, but you just need to specify the point. But okay, if you specify the point, like say this point is going to travel like 30 centimeters in a certain amount of time, but it's also rotating an angle, right? From this location to that location, it has rotated 90 degrees. It's the same point traveling and rotating, so the angle and then the distance, they must be connected. So everything angular must be connected to the linear quantities we defined before, right? And the relation is very easy to find. First of all, you just make use of this definition of the angle in radians, right? So if this is a point you pick, it's going to travel this distance in the same amount of time. It's also going to rotate this angle in the same amount of time. How are they connected? Well, now the distance is just the arc length, right? So the angle it travels is just going to be the distance the point travels divided by the radius of that point, okay? So the radius of the point, if you pick a different point on the rotating object, right? Because the rotating object is not always a perfect circle, right? So it doesn't have its own radius, right? But if you pick any point, that point is always traveling in a perfect circle, right? If you take a look at the rotating object in slide 4, right? This thing doesn't have a radius, this rotating object, but if you pick a point P, this point P, when this object is rotating about this point O, this point P is going to be traveling in a perfect circle, right? So this circle has its own radius, and if you pick a different point, it's going to have a different radius. That's why the distance is going to depend on the point, but the angle doesn't, right? Okay? And you can also use that to find out the relation between omega and v, the angular velocity and linear velocity. So all you need to do is this, right? So if I rearrange this equation, I will get this. So the distance travels equals the radius times the changing angle, right? And then if you plug that in, you would just get r changing angle divided by changing time. And if you put the changing angle divided by changing time together, that's just going to give you r times omega. So the v, the linear velocity and the angular velocity for the same point, they're also connected by this radius. And also, you can also show that the linear acceleration of that point is also connected to its own angular acceleration with the radius. So these guys, angle, linear velocity, linear acceleration, they are the same for any point, right? But the distance, the linear velocity, the acceleration of that point depends on the radius, so they are different. Okay, but anyway, these linear quantities and angular quantities, they're always connected by the radius of that point. Okay. Now we're going to do some practice. We want to practice this kinematic theory. Well, it's not a new theory, but we want to get used to these symbols. Okay. But first of all, let's take a look at the question, or the first part of this question, slide 5. A car tire is 40 centimeters in radius. The car accelerates from rest to this number, this velocity 55 miles per hour in 4 seconds. What is the tire's average angular acceleration? So if I want to find angular acceleration, this is something defined. It has a definition. So the first thing I would try, if I want to find like momentum, impulse, as I said before, the first thing I would try is a definition. Angular acceleration has a definition, so let's try that. I want to find angular acceleration. So I'll just do changing angular velocity divided by changing time. I do have the time in the problem, right? The car accelerates from rest to 55 miles per hour in 4 seconds, okay? But then I need the changing angular velocity, right? That's going to be final minus initial. Okay, but I don't have these two guys. Well, first of all, what is the initial angular velocity? Well, initially it's not moving, it's not rotating, right? It accelerates from rest. So initial velocity, initial angular velocity, both are 0. So this is 0, I don't need to worry about it. So the only thing I need to find is going to be the final angular velocity. How do I find the final angular velocity? I can try the definition. But now the definition is not going to work because I do have the change in time, but I don't have the change in angle, right? It just tells me that it accelerates from rest to 55 miles per hour in 4 seconds. It doesn't tell me anything about the total angle it has rotated. Then we can use the connection between the linear velocity and angular velocity, right? So these are the equations you can use if you want to connect linear quantities with angular quantities. I want to find the final omega, the final angular velocity. But I do have the final linear velocity, right? Because the problem says that it's going to accelerate from rest to 55 miles per hour. 55 miles per hour is a velocity. But of course, I'm going to convert that to meters per second. Right? I can't use this to find the angular velocity, okay? So once I convert this to meters per second, then the angular velocity, final angular velocity is going to be this guy divided by radius, because they're always connected by the radius, okay? They're always connected by the radius, okay? So I want you to try that. This is what we're going to do, right? Convert it to meters per second. That's velocity, linear velocity. But I want angular velocity. I'm going to use the connection between them, always connected by radius. Find the final angular velocity. Then, don't forget what we're doing. Plug it into the definition of the angular velocity, or angular acceleration. We can find that. Okay, first of all, okay, let me convert it to meters per second. So, let's see. All right, so it's gonna be okay. So that's the velocity in meters. Now I can go ahead and use this number divided by the radius, right? So the radius is given, right? The car tire is 40 centimeters in radius. Okay, so you can find the angular velocity, which is gonna be radians per second. Okay, so now you can go, don't forget, this is not the final answer, right? Now you can go ahead and divide this, changing angular velocity divided by changing time, which is 4 seconds. That's going to give you the angular acceleration, okay? Now let's take a look at the second part of this question. How many revolutions does the tire rotate? How many revolutions does the tire rotate? Okay, so how do I find the revolutions? Well, if I know the angle it has rotated, right, in radians or in degrees, right, then I can convert that to number of revolutions, right? Say, if I find that it has rotated 720 degrees, okay, that's gonna be 2 revolutions. Or if I found it has rotated 4 pi radians, okay, it has rotated 2 revolutions. So all I need to do is to find the angle, okay? And in this case, we're gonna do SI units. So we will find the angle the tire rotates in these 4 seconds, and then convert it to number of revolutions, okay? So that's what we're going to do. So now I want to find the angle. So I'm going to use the kinematic equations, right? So it's like finding the distance. If you want to find the distance the car travels in this problem, linear motion, you would just use the kinematic equations, right? So now let's see. I want to find an angle, so let's see this or this, right? Either one. So let's see which one do we use. Well, this is the better one because I do have the time, initial, and angular acceleration we just found, right? So if you plug numbers into this equation, you will find that I'm going to erase this. So initial angle is 0 because you can always call the initial point 0, right? Now the initial angular acceleration is 0 in this problem because it starts from rest. Now all I need to do is just do this. And the alpha, we just found it, right, in the first part. So the time is still 4 seconds. Now you plug numbers in, do the algebra yourself. You actually get radius. If this is a free response question, no, if this problem says that what is the angle the tire rotates, okay, I'm just going to leave it there. That's the angle, and it's in SI units. Perfect. But now the problem says how many revolutions does the tire rotate, right? So it's pretty much like a problem in linear motion. The problem asks how many miles does it travel? Okay, so I'm going to calculate the distance traveled in meters, but now you're asking me about miles. I'm just going to convert it to miles, right? So all I need to do is just convert this to revolutions. How do I convert it to revolutions? I'm just going to use this conversion, right? So revolution, you can also consider that as a unit for angle. So revolutions, degrees, radians, they're all units for angles. So, and then, so 1 revolution equals 2 pi radians. So I'm going to put 2 pi radians down here because I want to get rid of it. And put 1 revolution at the top, right? Okay, and then I can find the number of revolutions it has rotated, right? So in this case, it's going to be 19.6 revolutions. Okay, so that's the number for revolutions. So we used the second kinematic equation exactly the same way we did before, right? You just need to get used to this new symbols, okay? Okay, so we just finished that. Now we're going to talk about the cause of rotation, okay? So we're going to also define something which is similar to the cause of linear motion before, okay? Now take a look at the question I asked you on slide 7. So if there's a door, okay, and you want to open the door, when you open the door, usually you're just rotating the door, okay, about the hinge, right? Say there are 4 options here, okay? Which one is going to be the best option to open a door? You're going to apply a force at which location and with which angle, okay? Excuse me. I hope this is intuitive because we open doors every day, right? We open doors every day. Now tell me your right answer, okay? So I hope everyone gets the same answer. It's going to be A, right? So F1 is the best option because when I open a door, usually the handle is going to be on this side. Right? No, you can't see me over there, okay? But anyway, when you open the door, you're going to hold the handle. The handle is always on the other side of the door, and then you usually apply a force almost perpendicular to the door, and you feel that's the easiest, right? So that's intuitive. That agrees with our experience. Now let's compare all these options, these 4 options. So slide 8. What is the difference between F1 and F4? Okay, that's obvious. I hope that's obvious. It's gonna be the distance, right? You see F1 and F4, they're in the same direction. You apply the same force in the same direction, but F4 is closer to the hinge. F1 is far away from the hinge, right? Now the next slide. What is the difference between F1 and F3? F1 and F3, they act at the same point. So if that's a handle, okay, but what is the difference between F1 and F3? Well, of course, it's the angle between the force and the door, right? So that's going to be B. So that's the difference between them. Now let's take a look at slide 10. Okay. Okay, what would you do if the door is very heavy? Okay, which is going to be your solution? Okay. Please don't tell me that you select C or D. Okay, I know someone's going to select C or D. But say there's no button you can push. There's only one door to this room. Okay, so C and D, okay, out. But A and B, they both work, right? But they have the same idea. If the door is very heavy, you just need to apply a larger force, right? I know PHY is the best option, but if I can't open that, I can ask someone to help me, or I just push harder. Okay, so let's take a look at the summary on slide 11. In order to rotate the door, there are three things you need to consider if you want to find the best option. If you want to describe the ability of a force to rotate something. First of all, the force, of course, right? If you use a larger force, it's definitely easier to rotate something. Secondly, the distance also matters, and we have seen that, right? And then usually, the farther away from the rotating axis, the better the option is, right? And then the angle is also something you need to consider, and from our experience, the best angle is going to be always 90 degrees, okay? So now, okay, that's all intuitive, okay? That's based on experience. But I want to define something so that I don't need to always explain things using words, using my experience, using common sense ideas, right? We want to define something which has all these three factors, right? Like when we define momentum and impulse, right? I want to include all these factors. So the best definition, of course, you need to try which one is the best definition. And the best definition physicists found was the product of the force, the R, which is called the arm, but it's just a straight line you draw from the axis to where the point is applied. And also the sine phi angle. And the phi angle is just going to be the it's just going to be that angle between these two lines, the force line and the arm line, okay? So that's going to be the definition of torque. And then torque is the cause of rotation, okay? So that's another thing we define here. And we use a Greek letter tau, okay, to denote torque. Okay? So this guy, what is the unit for this guy? The force is in newtons, the distance is in meters, or the arm is in meters. So the sine phi is a pure number. So this guy has a unit Newton meters. We're just going to call it that. We're not going to give it a new name. Okay? So the force is easy, right? We're very familiar with force. The arm, okay, it's a fancy name, but it's nothing but a line you draw from the axis or pivot to the point where the force is applied. So you want to rotate something, there must be some axis or pivot, right? You draw a line from the axis or pivot to the point where the force is applied. It doesn't matter what case it is. It doesn't matter how weird it is. Draw that line. That's the arm, okay? A lot of people, when they see a problem, they're like, where's the arm? What does the arm mean? The arm is just a line you draw from the axis or pivot to where the point is, the force is applied. Then that's it. Use the definition. You can always find the arm, okay? You don't need to define arm in your own way. You don't need to figure out arm based on your own judgment. Just draw a line from the axis or pivot to where the force is applied. That's it. Okay? And then there's always an angle between the force line and this arm line. Because there are two lines, they always make an angle, right? And then you see that there's an image on slide 14 to help you visualize these three symbols: force, arm, and then the phi angle, okay? So in this case, this is let me draw it out. So this is a wrench, right? And then you're rotating about this center. So this is the pivot. So you are applying a force, say, in this direction, not like 90 degrees. So this is the arm you draw, right? Where is the pivot? This is the pivot. Where is the force applied? This point. Okay, draw a line, draw a straight line connecting these 2 points. That's it, okay? Okay, that's going to be the R. And then that's the direction. Then they make an angle, right? So you should, so strictly speaking, you should pick this angle because this is the direction of the R. You can extend it. This is the direction. That's not the direction. So when you pick the angle, you actually should pick the angle between this line, this big angle, not the small angle, right? But even if you say that I picked this angle, okay, I made a mistake, it's not going to make a difference, right? Because say if this angle is like beta, okay, what's the relation between these two angles? So beta is going to be 180 minus phi. And then there's identity in trig. The angle beta is going to be sine 180 minus phi for sure, right? Sine 180 minus any angle is going to be equal to sine of that angle. So that means when you pick the angle, okay, you don't have to be super careful, okay? Even if you pick the small angle or the large angle, doesn't matter. You sine it, you get the same number, okay? So as long as it's the angle between the force line and the arm line, you will get the right answer, okay? So you can either pick the small angle between them or larger angle between them, fine, doesn't matter. You always get the same number, okay? But if you calculate this torque, this new thing we define, okay? Just find these three guys, multiply them together, okay? A lot of people, they're afraid of new definitions. Don't be afraid of new definitions, okay? If I want to find this thing, just use the definition, find the three guys, multiply them together. That's it, okay? And it does have all these three factors we just discussed, right? The force is in there, the distance from the axis, which is the arm we just defined, and then the angle phi is there, right? Now sometimes you can see this term moment arm, okay, on slide 13. That's nothing but just a product, a new name people make for these two things, okay? So sometimes they call this d moment arm times phi. They would call this product moment arm. Then they would write this torque as force times the moment arm. But that's the same idea, right? Just a different notation, okay? But in this class, I'm just going to still use this. I'm not going to use this moment arm, this term at all, okay? We're always just going to do force times arm times sine phi to find a torque, okay? And then using torque, now you can explain why. So let's see if this is the best definition, right? So take a look at slide 14. Then using this definition, why is F1 is the best? So if say all these forces, they have the same magnitude, F1 has the same arm, right? Has the largest arm. F1 also has the largest sine phi, because the maximum value of sine phi is when phi equals 90. So that's why we use sine here, not cosine, right? Because if you use cosine, you put a 90 degree, you get a zero torque. It doesn't make any sense. It doesn't agree with our experience. Because our experience that 90 degree is actually the best option. 90 degrees is going to give us the best rotation effect, okay? So you put a 90 degree there, you get a maximum value for sine. So that's the best definition, okay? So F1, if you calculate the torque for F1, F3, F2, and F4, F1 is going to have the largest torque. So that's why this is a good definition. We can use this definition to describe the ability of a force to rotate any object instead of just using our experience, using our judgment, okay? And this definition also explains that why F2 doesn't work at all, right? Do you rotate a door by applying a force in that direction? You don't, right? You're just pushing the door toward the hinge. You're not going to open the door, okay? And if you do that, people are going to laugh at you. Hey, you're not going to open the door, okay? And then in that case, what would be the direction of the arm? So you will still draw the arm this way, right? So we can also see why this is a good definition. If you apply force in this direction, F2, you still draw arm from the pivot to where the force is applied. This is going to be the arm, right? And what is the angle between these two directions? 180, right? Sine 180, 0. So it doesn't matter what these two numbers are. You put a 180 in there, you get a 0. So 0 torque, 0 rotation. It is a good definition, right? So all I need to, if I want to compare different options, I just calculate this number and compare these numbers, okay? All right? So that's why so then this is a very useful conclusion, right? Any force, if it's a line that passes through the axis, it's not going to rotate this object, so it doesn't have any torque, okay? All right, so, and then strictly speaking, there's a nicer way to write torque as a vector. So torque is also vector. Torque is also vector. These two guys, they're also vectors, okay? So, and then torque is actually a cross product between the arm and the force, okay, strictly speaking. Because if you still remember the definition of cross product, which is on slide 15, okay? And then the cross product between two vectors, if I have like a vector and B vector, and then you make a cross product between them, you still get another vector, but this vector is going to have a magnitude which is going to be the product of these three guys, A times B, the magnitude of A times the magnitude of vector B times the sine theta angle, with the angle theta being the angle between them. Well, let's use phi. Okay. And then the direction is going to be right-hand rule, okay? And then there are distributive laws for cross product, but they're not commutative, okay? And then, so as I usually say, that these tools, like mathematicians, they invented a lot of tools, okay? So some of the tools may even seem like useless, okay? But then physicists, they realize when they study like real things in nature, they realize that, oh, these tools mathematicians they invented are actually very useful, because you can write a lot of things using the tools they invented, okay? So actually, the torque, the definition, the strict definition of torque is a cross product between the arm vector and the force vector, right? And you see that the magnitude of this guy is just going to be r times f times sine phi, which is the definition of the cross product. And the directions that will be weird. You're going to use right-hand rule, but in this class, we're not going to really worry about the direction of the torque or the direction of the angular velocity or angular acceleration. We're not going to worry about that. And even in this class, we're not going to really worry about this cross product. We're still going to just use this to calculate the magnitude, because we're only interested in the magnitude, okay? But this is just the formal definition of torque in vector form. Okay, so that's the definition of torque. Now, using that definition, you can actually find a very nice equation for a rotating object, okay? So what is that equation? Now I'm going to erase these kinematic equations. So take a look at the slide 17, okay? You can start with Newton's second law, okay? So I'm not going to prove that, okay, because it's okay. For any rotating object, you pick a point. You pick a point, right? A single point at that point, at any point you like. And then you apply Newton's second law in the tangential direction, not in centrifugal direction, because we already know in centrifugal direction, that's just centrifugal acceleration and centrifugal force, right? You apply this law, you do some algebra, and then you use this, you do it for every single object, and then you add all these equations together, okay? You will get a very interesting equation. You will get the net torque on this object, which is just going to be the sum of all the torques, right? And what is so there may be many forces rotating on this object, right? We're going to see examples, not just one force rotating this object, right? And then the net torque is always going to be equal to something like this. Okay, I'm going to also erase this. So it's going to be this weird thing multiplied by alpha. Alpha is the angular acceleration of this rotating object. When it's rotating, it definitely has an angular velocity, angular acceleration. It's like something's moving, it must have a velocity like 10 meters per second, or some acceleration like 2 meters per second square. Or sometimes like the acceleration is 0 if it's moving at a constant velocity. But anyway, it will have anything rotating, you will have an angular velocity and an angular acceleration at any point, right? And then you can derive the equation for any rotating object. So the net torque is just the sum of the torques, right? So there may be 3 or 4 forces rotating this object together. You just calculate torque from each force, add them together. So that's the left-hand side. That's what that torque means. And then on the right-hand side, you get this weird thing times alpha. Alpha is easy to understand, right? That's the angular acceleration. What is this thing? Because as I said, you're going to apply Newton's second law on every single point. So basically, you have an infinite number of points, right? And then you pick every little piece. So this little piece is going to have a mass. We call it mi. Okay, and this little piece is also going to have a radius from the rotating axis, right? This little ri, and this mr and ri, they're going to be different for different points. Okay, so I'm not gonna derive it here. So this is really weird equation, but if we make a definition, okay, because I just want to write this equation in a nicer form. And I don't like this guy. I'm going to define a thing, okay, called moment of inertia. Okay, so it's a very weird name, but I'm going to do this. Then you're going to see why we want to do this, right? Whatever this thing is, mi times ri squared, and then you can add them together. So you can add this number from every point. You will get a total number at the end, right? Doesn't matter. I'm just going to call this guy moment of inertia. Why do I call it moment of inertia? We're going to see that in a little bit. The units for this guy is just going to be kilograms times meters per second. So this is another thing we define. Very non-intuitive. The first time I learned this definition, I was like, what is this? Okay. mr squared, then you add them together. Well, this is not something you can find like a equivalent in your life, right? This is purely a definition. Why do we define it that way? If I define it this way, and let's rewrite this equation, I would get net torque equal, so this whole thing I'm going to replace it with this, whatever this I is, times alpha. Okay? This is exactly the same form as Newton's second law. What is Newton's second law? Net force equals mass times acceleration. So, and it's very easy to understand because acceleration is equivalent. The linear acceleration, angular acceleration is equivalent to the linear acceleration. The torque is the cause of rotation, which is also the equivalent to the force, because the force is the cause of motion. In linear motion, right? So the torque is equivalent to force. So that means this I, whatever it is, very weird, okay? But it's equivalent to the mass of a moving object, okay? So that's why we call it moment of inertia. And some books even call it rotational inertia. So it's like inertia, right? Because we know that mass is the measure of inertia of any moving object, okay? And you see that by defining this weird thing, we get a law which is exactly the same as Newton's second law. So that's why this is called a rotational analog of Newton's second law. So this is still Newton's second law in rotations, just with 3 different new symbols. Okay? Again, if you don't know what these 3 symbols mean, you don't know what F, M, A mean, you don't know them. I list these 2 equations for you. You will say, they look the same to me. You're just writing 3 symbols, and then 1 symbol equals the product of the other 2 symbols, right? So they are exactly the same equation. We are familiar with these 3 symbols. We know what they mean. Okay, these new symbols, well, they're a little bit weird to us, especially this I, very weird. Okay, the first time I learned this, very weird to me. Okay, but this is still like force, net force equals mass times the acceleration. Now, this is the angular acceleration. This is the cause of rotation, so net torque. And this I is like the rotational inertia of this object. When something has a big I, that means it's very hard to rotate it. When something has a very small I, that means it's very easy to rotate it, right? So this guy is equivalent to the mass in linear motion. We're more familiar with this, but this guy, whatever this definition is, it behaves like an inertia in rotation. Okay. And then take a look at the table on slide 18. You can see that we have pretty much defined everything. Okay, we have defined the equivalent to everything in linear motion. Okay, these are the things we defined so far. The angle is equivalent to distance. Angular velocity equivalent to velocity. Angular acceleration equivalent to a linear acceleration. Now this torque we define equivalent to force in linear motion. Force is the cause of angular motion. Force is the cause of linear motion. Force is the cause for acceleration, linear acceleration. So torque is the cause of rotation. Torque is the cause of angular acceleration. And this I we define is equivalent to the mass in linear motion. So use this table, use the connections between these variables to help you understand all these new things we define on the right. Okay, it's going to take you some time to get used to these new symbols, these new quantities we defined. Okay, and this I doesn't matter how weird it is. Okay, it can be calculated for regular shaped objects using calculus. So if you have a regular shaped object, you just do this. Okay? So we're not going to calculate I in this problem. So we are not going to worry about I in this problem, the moment of inertia. We're just going to look it up in the list. So take a look at slide 19. So all these regular shaped objects, the I's have already been calculated. So all we need to do, if I want to use this law, Newton's second law, this is still Newton's second law. Okay? We still call it Newton's second law. If I want to use this law, to find I is actually easy. Easiest. Why? Because we don't need to calculate I. And this list, it's going to be given on the test. So all you need to do is that, and we're just going to see these regular shaped objects in this class. So all you need to do is that, okay, what is the object in this problem? Oh, it's a cylinder, solid cylinder. Okay, I'm just going to find the I equation, the equation for the I for a cylinder, and then plug numbers in, find the I, and then go ahead and rearrange this equation to find things I need. So I is very weird, but when we solve a problem in this part, I is actually the easiest. You never need to worry about I. Just look it up, find the expression for that object in the problem, and plug numbers in. Okay? So this is the list of the objects we're going to see in this class. And you can also see that even for the same object, like the rod, okay, if it's rotating about a different axis, the I is going to be different, okay? So this is another difference between the rotational inertia and mass, right? The mass of the rod, no, it's not going to change, right? It's always going to be the same. If it's moving at 5 meters per second, 10 meters per second, no, it's always going to be the same. But the rotational inertia, because it depends on the radius, and the radius is the distance from the rotational axis to where the point is. Of course, if you rotate this object at a different point, the R is going to change. So the calculation, when you calculate the I, even for the same object, if you pick a different rotation axis, you will get a different number, okay? But anyway, you never need to worry about I in this class. You always just look it up, find the right equation for the object in the problem, just calculate this I, okay? the torque and alpha, they are the hard parts, okay? All right, so now let's take a look at a question here, okay? So we're gonna practice this law, Newton's second law in rotations, okay? So let's take a look at this question. And we can also do an experiment with this question. A uniform rod of length, okay, all symbols, right, slide 20. We're gonna just use all the symbols to do the algebra. So it has a length m, L, the mass m, okay, good. The rod is released from a rest at the angle theta, which is horizontal, okay? So that means you lift one end, okay? You lift one end and then let it go. We want to find the linear acceleration of the right end of the rod when it is released, okay? So this is a very weird question. So the rod is here, and you lift one end, you let it go. Of course it's going to fall, but it's not going to be in free fall because you're not just like holding two ends and let it go. That's going to be free fall. You can consider as like one particle, a point mass. In this case, this end is not moving, right? This end is, you can even fix that end, okay? You just lift the other end, this end is not moving, so let it go. And then when it's falling, okay, so this end is fixed, okay, it's pivoted, so it's not actually falling, it's actually moving in a circle, right? Because this end is fixed, so this end is actually going to be rotating, right? Actually, so we want to find acceleration of the right end when it's released. So we want to find acceleration at this point, okay? So this is very weird. If I want to find acceleration, the first law that comes to my mind is going to be Newton's second law, right? F equals ma. But in this case, this is not a linear motion. This is a rotation. So I have to use Newton's second law in rotation. This is still Newton's second law. Three weird symbols. That's fine. Call it Newton's second law. Okay, I can still use that. So I'm going to use that law to find acceleration. But wait a minute. That law is going to only help me find angular acceleration, right? But the problem wants to find linear acceleration. But don't forget, angular acceleration and linear acceleration, they're always connected by the radius of that point, right? So that's why the problem says find the linear acceleration of the right end. It has to specify the point for you, okay? Because the acceleration is going to be different if, say, I pick the point at the center, or I pick a point like 1/4 L from the other end, okay? So that means at the end, I have to do this. Don't forget this step, right? We still want to find the linear acceleration A, and then what is the radius of this point, the right end, when it's rotating? This is the center, right, when it's rotating, okay? So of course that's going to be L. If I pick this point. What if I say that find the linear acceleration of this point, the center? What is the radius you plug in? 1/2 L, right? Because the total length is L. The radius of each point, of a point you pick, that's going to be the radius, okay? Now the right end is going to be L. So this is easy. The last step is easy. Just don't forget that. Then the hard part is the first step. I'm going to use this equation. This is a very weird, but still Newton's second law. I want to find the alpha. By looking at this equation, how do you find the alpha? Well, I would just rearrange this equation, right? Alpha is going to be net torque divided by I. It's like acceleration equals net force divided by mass, okay? Don't be afraid of these new symbols. This is pretty much like acceleration. This is pretty much like net force. That's mass. Now, as I said, I, it's always the easiest thing to find in this part, because all you need to do, just find it in the list. So this is rod rotating about one end. What is the I should use? Okay, go back to slide 19. That's going to be 1/3 ml squared. So that's the I I'm going to use. So the I for this guy, 1/3 ml squared. See, that's it. Okay, if I have these two numbers, I'm just going to plug in, I will get number. But in this problem, I don't need numbers, I'm just going to work with the symbols. This is going to be the I. Okay, I is easy. Torque, it's hard to find, right? As I said, actually torque and alpha, these two guys are the hard parts. This I is always easy. Now torque, how do I find torque? Use the definition. Torque has a definition, all right? All these new things in this part, they have definitions, okay? You don't have to find torque using your own judgment, using your own theory. All I need to do is just find out the force on it, and then find the arm for the force. So this is arm, this is not always radius, okay? And then sine phi angle. Okay, so let's see. If I want to find the torque on this guy, how many forces on this guy? Only gravity, right? You see that once you let it go, gravity is going to pull it down. Well, it's not in free fall, but gravity is the only force on it. So where is the gravity? Now you can't ignore the shape of the rod. So gravity is here. Okay, I'm going to draw gravity here. And only gravity is on it, right? So, okay, so that's the force I'm going to plug in. Okay, this definition is very new, it's very weird, that's fine. If you want me to find a torque, I'm just going to find these three guys for you, multiply them together. That's it, okay? Now, what is the arm? What is the definition of arm? Everything has definition in this part, okay? A lot of new things defined, but they all have definitions. Go back to slide 12. What is the definition of an arm? You draw a line from the axis of pivot to where the force is applied. Okay? Let's draw a line from the pivot, which is going to be at this point, to where the force is applied. The force is applied at the center, right? Gravity is at the center. This is the R I'm going to use. What is this R? 1/2 L. Okay? That's the second thing I plug in, 1/2 L. Oh, it's using big M, but that's fine. The problem is using big M. Okay? So that's the second effect. Now the angle. Okay? Don't do that. Oh, there's a theta angle in the problem. I'm going to plug it in. Is that theta angle the angle you need in this equation? I'm not sure. Right? I have to draw the angle. What is this angle? As I said, this is the definition, right? This angle must be the angle between these two guys, right? Otherwise, why do you put them together? It doesn't make any sense to me. You tell me this is the definition of torque, but this phi is defined with something else, right? This is going to be a terrible definition. So the phi angle is going to be the angle between them, and as I said, because sine 180 minus phi is going to be equal to sine phi. So you can always pick any angle, the small angle or the large angle, you always get the same number. But you should always pick the angle between these two lines, the force line and the arm line. Where's the force line? This is a force line. Straight. Vertical. Where is the arm line? This line. Just along the rod. So which is the angle phi? This is the angle phi. Is this angle phi the theta angle from the problem? Oh, it's not, okay? Because the problem says this guy is going to make an angle theta with the horizontal. How do I use the theta angle to find the phi? Okay, phi is going to be 90 minus theta. Okay, so it's not like the problem gives me 30 degrees. Oh, that's going to be the angle I plug in if I see an angle in the in the equation. You should be careful, right? Now I'm going to, so this, if you still remember the identity, sine 90 minus angle equals cosine, right? So I can rewrite this thing a little bit easier. mg 1/2 L cosine theta. Now I'm going to plug it into this. Don't forget what we're doing. I want to use Newton's second law, this is still Newton's second law, to find the linear acceleration, angular acceleration, then multiply by the radius to get the acceleration, okay? Now let's do that. This is the torque. This is the I we found, right? Put them together, right? cosine theta divided by 1/3 ml squared. Now you can cancel things, right? Okay, one thing I need to emphasize, a lot of people in this problem, after we figure out this torque, they will say, why do you use cosine? You said it's going to be sine. I'm not changing the definition. It's because the theta angle in the problem is not the phi angle. We figured the phi angle is 90 minus theta, and I use the identity to replace the sine 90 minus theta with cosine theta. I'm not changing sine to cosine. I'm still doing sine phi, but now it becomes cosine theta. Now you see that, what do you get? You will get 3 halves and then g cosine theta over L, right? Okay? And don't forget, this is the angular acceleration. How do I find the linear acceleration? You're going to multiply that by L, by the radius of that point, okay? So you multiply that by L, what do you get? That's just going to cancel that L. It's just going to give you 3 halves g cosine theta, which is just going to be C. Okay, so that means you see that I only need the theta angle, so I can find the linear acceleration if you want me to give the number. Okay, and then I'm gonna show you the experiment in the next video. I'm gonna take a break now.